You may not close this.
I'm not going to close it. It's not
and it goes like this. The idea is, remember, we talked already about tangent plane. It's similar to a function in one variable. Let's say you have y equal f of x. So you have a tangent, and we use the tangent to approximate as linear approximation. We come up with equation of a line that is a tangent at a point, and we say that near that point, instead of calculating the value of the function at this point, which sometimes will be uncomfortable, we can calculate the value of the line of the linear equation at that point, and in most cases it will be much easier. The same way we can treat a surface. If you have a surface, let's say surface S is z equal f of x and y, and you have a point. Let's say the point is A and B, the x value and the y value, and there is a tangent plane to the curve. So let's say my knuckle is a point and my hand is a surface. Then at the knuckle there is a plane, and we're going to say that this plane is a tangent, plane. In other words, on this plane there is a tangent in many directions. We can have infinitely many directions. Of course, we can choose a comfortable direction. Will be either the x or the y, but essentially any tangent to the surface at the point will be on that plane. And later on we'll use this plane, which the equation in plane is a first order equation. In other words, you don't have anything squared. You have x and y and z in it. We can use this to approximate the value of, let's say, z at this point of the surface. Okay, makes sense? So suppose surface S is given by the following function. And the function will be z equal f of x, y. Okay, and we let the point P, and I'll use x sub 0, y sub 0, and z sub 0 be a point on S. So we have, if x equals x sub 0 and y equals y sub 0 are vertical planes. Okay, so we're going to say that the vertical planes x equals x sub 0 and y equals y sub 0 intersect the S, and as they intersect, if you have a surface and you have a vertical plane, let's say this is x equal a constant, this will be y equal a constant, then as we intersect, we trace a curve, and for each vertical plane, x equal x sub 0, y equals y sub 0 will have its own curve. So we're going to say that these two vertical planes intersect S by two curves, two space curves. We call it C1 and C2. Okay, so now we have a curve, and at this particular point, x sub 0, y sub 0, z sub 0, we can draw a tangent to the curve, and we're going to say that such that T1 and T2 are the corresponding corresponding tangents to C1 and C2 at P. Again, P is x sub 0, y sub 0, z sub 0. Okay. So, as I said at the beginning, the tangent plane is a plane that contains all possible tangent lines. So contain T1, T2, and all other possible tangent lines to the curve, the surface S at the point P. All right. So, having said that, what is the equation of a plane? Well, the general form, the general equation of a plane, it's a surface. It's a surface, so it's S. Okay, the general equation of a plane, actually, is spelling here. Passing through a point x sub 0, y sub 0, and z sub 0 is given by, do you recall what will be the general equation? Well, for a plane, you're talking about surface, but for a plane, it will be some coefficient A times x minus x sub 0, some coefficient B times y minus y sub 0, plus some coefficient C times z minus z sub 0, and all of it equal to 0. That's an equation of a plane. And the two girls in the middle, shut up. Okay. Notice that x, y, and z are all linear, all first order, and that's what tells you that you have a plane. Okay, the surface, of course, may have quadratic, cubic, whatever higher order. Now, if you divide both sides by c and solve for and isolate z, so divide both sides by c and solve for z, then you'll end up having z. Remember, we divide by c, so we'll have z equals z sub 0 plus a times x minus x sub 0 plus b times y minus y sub 0, where because we divided the uppercase A, B by the uppercase C, the new coefficient A is what we had before, divided by C, and the new coefficient B, lowercase, will be what we had before, divided by C, like so. Okay? And this is a little bit more convenient equation of a plane. For a particular value of x that equals x sub 0, if x equals x sub 0, in other words, if you are the point, then we have z equals z sub 0 plus b times y minus y sub 0. And this is just an equation, a point slope equation in one unknown, y. Likewise, if y equals y sub 0, this term disappeared, and we have z, which you can treat z as f of x, equals f of x sub 0 plus a times x minus x sub 0, where a is the derivative with respect to x, and b will be the derivative with respect to y. So this is a combination of two point slope form of a linear equation. Okay? So let me write a comment to that effect, and we're going to say the following. If x equals x sub 0, we have the point slope form of a linear equation. We'll have z equals z sub 0 plus b y minus y sub 0. Likewise, if y equals y sub 0, we have z equal z sub 0 plus a times x minus x sub 0. Right? We can put those two together and we come up with a theory. Well, before we'll go and have the theory, we can say the following. Where a will be the derivative of z with respect to x, and b will be the derivative of z with respect to y. Okay? And this will lead us to the following theorem. Start like this. Suppose del f del x and del f del y are continuous partial derivative of f of x y, then the tangent plane to the surface z equal f of x y at P, where we have x sub 0, y sub 0, z sub 0, it's given by, and here is the result. We're going to say that z equals z sub 0 plus del f del x at this particular point actually we can remove that z sub 0 because z is the dependent variable and x and y are the independent variables, and here we'll have x minus x sub 0 plus the partial derivative of f with respect to y at x sub 0 y sub 0 times y minus y sub 0. And you can see that this theorem gives you the equation of the plane as a sum of two linear equations, 2-point slope form of the same linear equation. We can modify it a little bit. Okay, So modify let P equals the point A, B, C, like so, and of course Z is f of A, therefore Z sub 0 is f of AB, and then we're going to say that f Z equals f of xy, okay, going to equals to f of AB plus del f del x at AB x minus a plus del f del y at AB y minus b. A little bit, well, it's the same thing, but instead of x sub 0, y sub 0, and z sub 0, we use the AB. But notice that this lead to linear approximation or linearization of this of the tangent plane.